Welcome back to Fat Mama Physics. Today we're going to look at the Doppler effect and specifically this particular equation here, which I will explain how we use it and how we derive it. At this point, you should already know that we get the Doppler effect from either you have a moving source. Let's say I have a moving source towards an observer. You will hear changes in the frequency that's observed by you as an observer. If the source is approaching you, you hear a higher frequency. As the source is moving away from you, you hear a lower frequency. Typical of, say, you have an ambulance or a siren going past you on the road. This both happens in sound waves and in light waves. But this particular video is just focused on how the derivation works and a little bit about how to use the equation itself. So let's start off with the equation here. So we have f naught, or it looks like a 0 on the bottom. Another way how you might see this is f with a prime. So that means this is the frequency that is observed by someone else, by the observer. Then you have f of s. This is the frequency of the source, and that is unchanged regardless of the source is moving. Whoever's moving, it is the original frequency produced. C is the medium speed of the wave in that medium. So typically it could be light, it could be which is 3 times 10 to the power of 8 meters per second, or speed of sound about 330 meters per second in room temperature air. Then you have V of naught and V of S. This is the velocity of the observer. Sorry, VO is the velocity of the observer, O for observer, and S for source. Okay, and the positive and the negatives I will explain as we work through the derivations. But typically, I don't tend to memorize whether it's positive or negative. I remember, or I look at how logically it would affect the frequency, and that's how I decide if it's going to be positive or negative when I'm using it in my equation. Okay, so this first part of this video is deriving the portion of the equation that is this, and that has to do with the moving source. So if the source is moving and the observer is not, then why do we get this part of the equation? Okay. The second part of the video, I will focus on, it's missing here, a moving observer. So this should say moving observer here, okay? And then this is how we derive the upper part of that equation. So that's how they maintain separated. I just read in an IB textbook, or the latest one for the newest curriculum, that you will not be tested when both observer and the source are moving at the same time. So lucky for us. So without further ado, I'm going to start the derivation for the moving source, or how we get this portion. So here we go. Get rid of this, get rid of this. Before we start the derivation, I just want to plant a visual in our minds. So this is a great simulation I found. I'm just going to play or start the simulation. So here I have a source emitting waves of, with a wave, you can see the wave fronts, and the distance between the two wave fronts is your one wavelength. Here I have a microphone, which is going to measure the frequency. So every time you hear a tick, or the frequency of the ticks, we're going to tell you the frequency. I'm going to start this object. I'll make this object move. And then if I have a moving source, we can see that the wave fronts in the front of the moving source are squished. So then from that, hopefully we were able to see the fact that, so I'm going to pause that source. Hopefully we were able to see that the microphone that is in front is going to see the wavefronts more frequently than if it were behind the source, okay, in which every time every time a wavefront is emitted, is kind of trying to catch up to the previous one that's hitting the microphone. So if you see that again, it's got that extra distance to travel. So this is what, and the perceived difference, or the difference between the two wavefronts, will change the perceived wavelength and therefore the perceived frequency. One thing that maintains constant is that the speed of the medium will be constant in the same medium, okay, regardless if it's for the source or if it's for the of the observer. So that being said, let's go back to here. We'll show what that looks like. So let's say I have a source and it's emitting sound, and over here I have a person, an observer, who is stationary. Luckily, we don't have to worry about when both of them are moving. Stationary observer. When we have this source, we can see how, actually, if I just made this source stop moving, we can see how the wavefronts maintain a constant distance between one another as they are moving away from the source. So what that looks like, it looks like this. So I'll use black for the source that is not moving. If it is moving forward towards the observer, then I'm going to draw everything that is moving in blue. Let's say it is moving forward with a speed of Vs. Then what's going to happen is that wavefront is going to get squished. So before we see the effect, there's a couple of things we need to write down for the original wavelength. The black ones, as we see, are the non-moving source. We know that the original speed of the wave within the medium is C is equal to the frequency of the source times the original wavelength. And I'm just going to label this original wavelength, which is this one here. This is the original wavelength itself. I'm going to express this in terms of period, in terms of time. I'll show us why later. We do know that frequency is equal to the inverse of the period. So this then becomes this. I get the wavelength over the period. If I want to express this in terms of wavelength, okay, I'll move this away, then this is going to be the wavelength is equal to the source, the speed of the source in the medium, times this period. I'm going to need this later when we do some derivations. Okay, so essentially this entire length is equal to CT times the period. Now, if your source is moving, that means this original wavefront would be scooched forward by this much. And this distance right over here, that's the extra space that's traveled in the span of one period by that particular wavefront. So after one period, this next wavefront by x, which is equivalent to the speed of the source, Vs, times the time of which that happened, which is one period. So that's the extra amount of distance traveled of that wavefront due to the moving source. Now what that means is this over here, this is the perceived wavelength by the stationary observer. It is now, the two wavefronts are now closer together. So this shortened wavelength is what is observed. I'm going to call this VO for shortened wavelength. Okay, so now that we see that this entire distance as the full original wavelength is made up of this extra distance traveled by the wavefront and the shortened observed wavelength. So if I write this together, I get the observed wavelength, or, I mean, I could either do plus or minus, but I want everything in terms of observed wavelength because that's what I'm writing everything as. So this lambda naught, or the observed wavelength, is going to be equal to the entire wavelength minus the extra distance that is traveled due to the moving source. And if I put everything together, it's going to look like this. I get the V naught, sorry, not V naught, the lambda naught is equal to, we know that the lambda here is CT, so I write CT instead. As for the blue, this is going to this is VS times the period, so I'll add it in there too, minus VS period. Now, this is where the rest gets a little bit mathy. Let's get rid of that just to make it clear. Then I'm just doing a bunch of math. First step is to move the period to one side of the equation, or sorry, to isolate the to factor out this period. So I get period on the outside, I get C minus VS. In fact, I can even change this V naught to C over frequency. That's going to be the original speed of this sound or speed of the wave in the source, divided by F naught, or the observed frequency. And likewise, I can do the same thing for this period. This is the period that's associated with the original frequency. So I can also get rid of this period and then sub in 1 over frequency as well. And this Fs, that's going to be the frequency of the source, since the period is the same period that we're talking about in term that's correlated with the original frequency of the source. Now the next part is just playing around with the equation, including I'm going to take the reciprocal of both sides of the equation. And after I do that, I'm going to switch over to a different color here, just so the rest of it is different. I get F of naught over C. This is going to be equal to F of S, which I'm going to put on the side here. Then C minus VS is going to be on the bottom of the equation. Okay, so that's what's going to look like. I'm also going to move this C up here to the top. Then that's just going to give me something that looks like pretty much this equation that we see here. But I'm going to take one extra step. So this is the observed frequency is equal to the frequency of the source times, all in brackets technically, the speed of the wave in the medium divided by C, same thing, minus the speed of the source. But keep in mind that we used a negative sign because the source was moving towards the observer, which means that if you want it where the source is moving away from the observer, then this instead would just be plus for source moving away from the observer. And that is summarized up here, which I have VS, positive when moving away and negative when moving towards. And that kind of makes sense because if your source is moving towards you, you're going to get a higher frequency. And if you subtract a number on the bottom of your denominator, it makes your denominator smaller. And that as a result, this whole number here, this fraction, is going to turn out bigger. A bigger number times your source is, of course, going to result in a higher observed frequency. On the other hand, if you're adding a number in your denominator gets bigger, then your whole number gets smaller. So this is kind of what I do when I do these questions, is I don't memorize the plus and minuses, I just look at what makes sense. And then that goes back to the imagery of what the wavefronts look like when they're moving towards and away. Okay? So that being said, this concludes the first part of the Doppler effect derivation. The second derivation, which is below, is I'm going to have a moving observer instead of a moving source. So thank you for your patience and following along with the video. Maybe I'll see you for part 2. Otherwise, good luck with your IB exams and studying. Take care. Bye-bye. Fat Mama Physics signing out.